Our discussion so far shows that among all spanning sets for a vector space, the most important are the minimal spanning sets, because they are the ones that provide essentially unique representation. And the minimal spanning sets are precisely the linearly independent spanning sets, which is a fancy way of saying they have no span redundant vectors. Everything in the set contributes to the span. This theorem, then, which kind of summarizes what we've discussed, is a cornerstone theorem in linear algebra. Let B be a non-empty set of non-zero vectors in a vector space V. The following are equivalent. B is linearly independent and spans V. Keep in mind that V is just a vector space, therefore it could be a subspace of another vector space that we're studying. So this applies to subspaces as well as to the vector spaces in general. B provides essentially unique representation for all vectors in V. B is a minimal spanning set for V. B is a maximal linearly independent set. This is a new one. Okay. So this means that B is linearly independent and no proper superset of B is linearly independent. Any set of vectors that satisfies one of these, and therefore all of them, is called a basis for the vector space. Oftentimes a basis is defined by number 1 here, a linearly independent spanning set. There's no particular reason why you have to choose that as your definition, and so since I didn't want to commit, I just simply said any subset that satisfies these 4 properties, any one of these properties, and therefore all 4, is a basis. Well, we've already seen that 1, 2, 3 are equivalent. All we have to do is tie in number 4. So let's show that 1 implies 4, that a linearly independent spanning set has to be, in fact, a maximal linearly independent set. If B was not maximal, then there would be a proper superset, let's call it C, of B that is also linearly independent. And it would span because its subset B spans. Well, now we have a linearly independent spanning set, so all 3 of these properties hold for this set C, and therefore C is a minimal spanning set, but that is a contradiction to the fact that B, which is a proper subset of C, also spans. So 1 implies 4. Conversely, if B is a maximal linearly independent set, then it must also span, because if it didn't, there would be a vector little v not in the span of B, and then an earlier theorem told us that we can toss in that new vector into B, make a larger set that's linearly independent, and that contradicts the maximality of B as a linearly independent set. And so 4 implies 1. because the basis for a vector space may be infinite, we will write an arbitrary basis in this form, using an index set as an indexed family of vectors. Actually, finite bases are the nicest in many ways. Countably infinite bases are not bad. Arbitrary, the uncountable bases begin to get a little bit difficult to deal with. But we can characterize finite and countably infinite bases in terms of direct sums. If we have vectors v1 through vn forming a set v1 through vn, this will be a basis if and only if v is the direct sum of the subspaces generated by each vector in the set. And a similar thing happens for countably infinite sets. This will be a basis for v if and only if v is a direct sum of the sequence of subspaces generated by the individual vectors. And we'll leave this for you to prove. Many common vector spaces have what is referred to as a standard basis. I guess because often it's the simplest basis to use, but it's generally by no means the only basis, and oftentimes it's not the appropriate basis. Here are some examples. For the vector space Fn, which includes Rn and Cn, the standard basis is the set of vectors E1 through En that consist of the ordered n-tuples with a single 1 and all zeros everywhere else. I'm going to try to reserve the notation little e sub k for this basis and for one other basis. Also, we will reserve the notation script s sub n for the standard basis in Fn. The notation doesn't indicate what the field is, so that will have to come from the context. A notation such as Sn of f would be more complete, but it gets a little bit cumbersome. Analogously, as we discussed before, this sequence space is the set of all infinite sequences with finite support under component-wise operations. This is what is called the standard basis for this vector space, and it looks pretty much like the previous case, but they are infinite sequences now with a single 1 and the rest zeros. The polynomial space has standard basis consisting just of the powers of x. The vector space of m by n matrices over F has standard basis consisting of matrices of this form with a single 1 and all zeros everywhere else. So this is what it looks like for M2 of F. These are the standard basis vectors. And I don't know, just for fun, I guess I threw in this example. The set of polynomials of this form we've seen already span, or I mentioned they spanned, I didn't prove it. They are also linearly independent, and therefore they form a basis for the polynomial space. Well, we are now ready to discuss the question of the existence of bases for a vector space. The trivial vector space does not have a basis because it has no linearly independent sets of vectors. But every non-trivial vector space does have a basis. And to prove this theorem, we need Zorn's lemma, which we discussed in an earlier video and is in Appendix B of the book. Actually, we can prove a little bit more than just the fact that every non-trivial vector space has a basis. If V is a non-trivial vector space, and if we have two sets, I and S, subsets of V, I is contained in S, I is linearly independent, and S spans V, then there must be a basis in between I and S. And this has some important consequences. First of all, it tells us that every non-trivial vector space does have a basis. But it also tells us, by taking S to be equal to V, that every linearly independent set is contained in some basis. In common linear algebra parlance, we say that every linearly independent set can be extended to a basis. It also tells us that every spanning set contains a basis. So those are two very important consequences of this theorem. As to the proof, to show that there is a basis that lies between I and S, all we need to do is show that there's a linearly independent set, B, containing I, whose span contains S, because the span of S is all of V. So, to be a little clearer perhaps, if S is contained in the span of B, then the span of S is also contained in the span of B. But the span of S is all of V, and so B also spans V and is therefore a basis. So, if such a set exists, a linearly independent set containing I whose span contains S, it will belong to this family. It'll be a J here between I and S, and J will be linearly independent. If B exists, it's among this family. J would have the special property, or B would have the special property that its span contains S. So that we're looking for a member of this family with a pretty large span. So our best shot at finding that is to find a maximal member of this family. And hopefully the span of that member, let's call it M, the span of M will contain S. In fact, it will, because if it did not, there would be a vector little s in S that wasn't in the span of M. But we can then, since M is linearly independent, we can enlarge M with the vector little s, and that will still be linearly independent. We have a theorem that says as long as little s is not in the span of M, the larger set is still independent. Therefore, it belongs to this family, and that contradicts the maximality of M as a member of this family. So all we need to do is show that this family has a maximal member. And that's where Zorn's lemma comes in. We know this family is non-empty because it contains I. If we take a chain of members in the family, what about the union? We need to find an upper bound for the chain. If you look at the union, because we are dealing with a chain of linearly independent sets, we also had a theorem that says their union will be linearly independent. And because every member, capital I sub k here, is that what, I think I gotta fix that, I sub k. Every one of these I sub k's, it lies between I and S, so does the union. So it's linearly independent and lies between I and S, so it belongs to our family here. It's obviously an upper bound for the chain, and so every chain in this family has an upper bound, namely the union of the chain. And so according to Zorn's lemma, the family does contain a maximal element, and we're done. Just as an aside, if S, the spanning set in question, happens to be a finite set, we don't need Zorn's lemma. We can prove this theorem directly, you might say. And I'm going to let you ponder how that would be done. In my experience, most undergraduate linear algebra books do not discuss Zorn's lemma. I'm sure there are some that do. I haven't seen them all. There's a million of them. And so this theorem would be stated only for finite spanning sets, or at least a proof would be given only for finite spanning sets. So that's what I'm asking you to think about. It's only a short paragraph long, really. This theorem is very important. We will often be in a situation where we have a subspace S of a vector space V, and we want to take a basis B for the subspace and extend it to a basis for the whole space. Very common. And so you're going to see this quite often, that a basis for S can be extended to a basis D for V, and we can write this. So the set script C are the additional vectors required to upgrade B to a basis D for the entire vector space. And this is a disjoint union because you're adding vectors that are not in B already. You wouldn't, then this wouldn't be independent. Also, the theorem has a corollary that is sometimes quite useful. If V is a vector space and I is a linearly independent subset of V, then any spanning set S for V It may not have anything to do with I. It doesn't have to contain I. Any spanning set will have a subset that you can use to augment I to get a basis for the whole space. And the proof is quite short. If we take the union of I, the independent set, and the spanning set, we will get a spanning set. And it, of course, will contain I, which is independent. So we have the situation here of the statement of the previous theorem. There's a basis in between these two, the independent set and the spanning set. Well, what does a set look like that lies between these two? It's I together with some vectors from S. In other words, S naught. Now that we can extend linearly independent sets to bases, we can provide an alternative proof for a theorem we gave some time ago concerning the existence of complements for subspaces of a vector space. The proof we gave before used Zorn's lemma directly. The proof I'm about to give you does not use Zorn's lemma directly, but keep in mind that the fact that every non-trivial vector space has a basis requires Zorn's lemma. In fact, it's equivalent to Zorn's lemma. So we're not getting away without using Zorn's lemma. We're just shifting it to the earlier theorem. So this proof won't mention Zorn's lemma, but in fact, behind the scenes, Zorn's lemma is required. Okay? So, any subspace of a vector space has a complement. We'll call it T. First of all, if the subspace is trivial, then we can take T equal to V. So we may as well assume that S is non-trivial. Therefore, we can take a basis B for S and extend it to a basis D for the whole space V. And then we can let this subspace span by C, we'll call that T. And we can show that T is in fact a complement to S. So the first thing we want to show is that S and T are essentially disjoint. Well, if we take a vector in the intersection, then there are scalars, the A's and the B's. Because V is in S, it's a linear combination of the U's. The U's are the elements of the basis for S. They're the where to go, B. Okay. And because V is in T, and the C here is a basis for T, V is a linear combination of vectors from C. Okay, so the UI's are in B, and the VJ's are in C. Now we just put everything on one side. This is a linear combination equal to 0, but the U's and the V's all belong to the basis D for the whole space, so this set is linearly independent, and so any linear combination that equals 0 must be trivial. So the AI's must be 0, and the BJ's must be 0. and so the vector little v must be 0, which means that the intersection of S and T is just trivial. So the sum here is direct. Moreover, since D is a basis for V, any vector little v in V is a linear combination of the vectors from D. But D is the union of B and C. So by rearranging the terms, reindexing, whatever, we can write little v as a sum of vectors, a linear combination of vectors that come from B plus a linear combination of vectors that come from C. In other words, it's in this direct sum. Therefore, all of V is in the direct sum, and T is a complement of S. As far as we know at this point, it might be possible for a non-trivial vector space to have bases of different sizes, but this cannot happen. And I'm going to give you first a proof that works when the vector space V has a finite spanning set. And then we'll look at the general proof. And I'm splitting this into two parts because the general proof requires a little bit of arithmetic of cardinal numbers, whereas this case does not. Also, this is a proof that is somewhat famous, and I think you should see it. So here is the statement of the theorem. V is a vector space, and V1 through Vn are linear. This set is linearly independent, and the vectors S1 through Sm span V. Then n is less than or equal to m. The number of vectors in any linearly independent set is less than or equal to the number of vectors in any spanning set. That's what we're going to prove. And from that, it will follow very easily that as long as the vector space V possesses a finite spanning set, all bases will have the same size, and we'll see how that follows after we look at this proof. So here's the way it goes. We take the spanning set, we write it down here, vertical bar, write the linearly independent set. Let's call this the first list and the second list, separated by the bar. The plan is to start moving vectors from the second list to the first list, but always preserving the fact that the first list spans and the second list is linearly independent. If we pull vectors out of the second list and move them to the first list, this will always be independent because any subset of a linearly independent set is linearly independent, a non-empty subset. If we toss in a vector on this side, the list still spans. It's just bigger, it still spans. So here's how it goes. Take V1 and move it to the front of the spanning list, the first list. Still independent over here. Over here, this is, the V1 is a linear combination of the S's. So there is a non-trivial dependency among these vectors, that linear combination certainly has to involve at least one S. And so we can isolate that vector, that S vector, and write it as a linear combination of the remaining vectors in this list. Therefore, it's span redundant for this set. And we can toss it out, have the same span. So it could be any one of these S's, but by re-indexing we can assume it's S1. So we've thrown out S1. We have V1, S2 through SM, V2 through Vn, and we still have spanning set, independent set. So we'll do it again. Take V2, move it over, still independent on this side. On this side, there is a linear dependency over here because we had a spanning set, we tossed in another vector. But the linear dependency has still got to involve at least one S. Otherwise, it only involves the two V's, but the V's are linearly independent, so they have no linear dependencies. So again, we can grab one of these S's, which we'll assume is S2, and throw it out, and still have a spanning set. So we can continue to do this, move vectors over, and eliminate one of the S's, and still have a spanning set here, and an independent set here. We're trying to show that we're trying to show that n is less than or equal to m. But if it's not, if m is less than n, notice what happens. We will exhaust all of the S's, they'll all be gone, before we have moved all the V's to the first list. So we'll end up with something that looks like this. But we now have a big problem because this is a spanning set, but the whole works is linearly independent. So these vectors cannot represent any of these by linear combination. None of these is a linear combination of any of these because the whole set is independent. Both lists together, linearly independent, and that's a contradiction. So we must have n less than or equal to m, which is what we're trying to prove. Now we can rush to this corollary. If a vector space V has a finite spanning set, then any two bases of V have the same size. Because if we have two bases B and C, we can think of B as linearly independent and C as a spanning set. So the size of B is less than or equal to the size of C. But we can reverse the roles of B and C and think of B as a spanning set and C as an independent set, get the reverse inequality, so the two sizes must be equal. Well, let's take a look now at how the proof would go if we don't assume V has a finite spanning set. Any two bases for a vector space V have the same cardinality. First of all, if there is a basis that's finite, we're back to the previous theorem. So we can assume that all bases for V are infinite sets. So let's say we have two bases B and C for V. And again, they're infinite sets. we want to show they have the same cardinality. Any vector, little c, from the C basis can be written as a finite linear combination of vectors in the B basis. So let's say little c is in the span of B sub c. I'm indexing by this vector. Because if I change this vector, I may get a different subset of B. But the point is, B sub c is finite for all vectors in the basis capital C. So, capital C is then a subset of the span of the union of all these finite sets, right? Because every vector in C is in the span of this union. In fact, it's in the span of one of these sets alone, therefore it's certainly in the span of the union of all these sets. But C is a basis for V, and so its span is contained in this span. In other words, V is contained in this span, the span of the union of these finite sets. But of course, this union is a subset of the full set B. But now we see not only is it a subset of B, but it spans V. Well, B is a basis for V, therefore it's a minimal spanning set. So this union has to equal B. This is really the key observation, using the fact that B is a minimal spanning set. Now we come to the cardinal arithmetic. B here is the union of this many, cardinality of C, finite subsets. We're indexing by C, so there are this many terms in the union, if you want to say it that way. We don't know how big these sets are. We only know they're finite. But that tells us that the size of these sets is bounded by aleph naught. And we had a theorem, it's in the appendix, that would tell us then that the size of B is the size of this union. And what we can do is take an upper bound for the size of each set, aleph naught, and multiply by the number of sets in the union, cardinality of C. That will give us an upper bound on this size, on this cardinality. But we also know from cardinal arithmetic that the product of two infinite cardinals is the maximum of the two, and since aleph naught is the smallest infinite cardinal number, and this set, by assumption, is infinite, we get C. We get the size of C, excuse me. So the size of B is, or the cardinality of B is less than or equal to the cardinality of C. And then we go through this argument again, reversing the roles of B and C to get the reverse inequality, and the Schroeder-Bernstein theorem tells us then the two cardinalities are equal. This proof's a little rough going if you're not used to cardinal numbers. So you have a couple choices. I doubt very much that many undergraduate linear algebra books would give this proof, because they would have to discuss cardinal numbers to some extent. So you could just simply skip this proof. Your other choice is to go through it enough times, maybe refer again to the video on cardinal numbers until this makes sense. It's up to you. But you definitely should remember the theorem, the statement of the theorem. If not, it's proof. I don't need to say non-zero vector space here because the zero space doesn't have two bases, so we don't have to worry about that. Well, that is just the result we need in order to define the dimension of a vector space. The trivial space, by definition, has dimension 0. If V is non-trivial, then its dimension is the cardinality of any basis, because they all have the same cardinality, so we can take any basis. So if that cardinality is kappa, the cardinal number kappa, then we would say that V has dimension kappa, or is kappa dimensional, and write this. Kappa could be a natural number, could be a finite cardinal. Most of the time for us it will be, but it doesn't have to be. A vector space that has finite dimension is said to be a finite dimensional vector space, and all other vector spaces are infinite dimensional. Non-trivial vector spaces can be classified into 3 groups based on the size of any basis for the vector space. We have the finite dimensional vector spaces, the ones that have a finite basis. We have the countably infinite dimensional vector spaces, those that have a countably infinite basis. And then the uncountably dimensional vector spaces. And those have an uncountable basis. So we've seen examples already of bases, the standard bases for several vector spaces. The Euclidean type vector spaces, Fn, have a basis of size n and are therefore n-dimensional. The matrix spaces of matrices of size m by n also have a standard basis of size m times n. So that's the dimension. The polynomial spaces have countably infinite dimension because the powers of x are form a basis, and that's pretty easy to show. The sequence space of sequences with finite support have countably infinite dimension. It's a little harder to produce or to show that a vector space has an uncountable basis. Here's an example, and is the full sequence space of all infinite sequences over the real numbers. To show this has uncountable dimension, I'm going to show you an uncountable subset that is linearly independent. It won't be a basis, but it'll be linearly independent. And so it can be extended to a basis, which means at least one basis, and therefore all bases are uncountable. For every positive real number, consider call it A, consider the sequence S sub A, which just consists of the powers of A. And let I be the set of all such sequences. So this is an uncountable set. And we can show that it is linearly independent. And as I said, once we've done that, we know that this vector space has uncountable dimension. To see that I is linearly independent, suppose it's not. That means there must be a finite sequence of real numbers, I can organize them in increasing order. They're positive real numbers, and I'm going to write the sequences that correspond to them, denote them by S sub k rather than S sub a sub k. So we have these n plus 1 sequences that are linearly dependent. And we can arrange it by not including any sequences that are irrelevant to the dependency. So in other words, there is a set of non-zero coefficients, C sub k, for which the corresponding linear combination of these vectors is 0. And again, the coefficients are non-zero because if there are any 0 coefficients, I just delete this sequence from the list. This is what it looks like when you do the separate components. So the first component of this linear combination is the linear combination of these a sub i's, looks like that. The second component will be the linear combination of the a sub I squared, and so on. So for any positive integer m, this sum must be 0. Now we divide this by a sub n, which is a positive number. It looks like this. Break out the last term. A sub n over a sub n is just 1, so this is c sub n. These are the other terms. But a sub k is less than a sub n for k less than n. So in the parentheses here, we have a positive real number less than 1. So what happens is we send m to infinity. We let m increase without bound. This sum is going to go to 0 because it's a finite sum, and each term goes to 0. All we're left with then is Cn equals 0, which is false. All the c's are non-zero. That contradiction means that the set I is linearly independent. That was a bit of work just to produce a linearly independent uncountable subset of this vector space. I don't even know how to produce a basis. I've never seen one. The problem is these vector spaces are so large that uncountable bases, which must exist, are just too complex to deal with. What does one do in situations like that? Well, the answer is that for some infinite dimensional vector spaces, we can define convergence. In particular, normed vector spaces. The norm allows us to define convergence of sequences of vectors, infinite sequences of vectors. And so it may be possible to produce a useful set of vectors with the property that every vector in the vector space is a limit of an infinite sum of these vectors. A limit of partial sums, in other words, an infinite sum. But that's taking us out of the realm of abstract algebra and into the realm of analysis. In particular, functional analysis, a branch of mathematics that deals with normed vector spaces of which Hilbert spaces and Banach spaces are special cases. So that's a whole separate subject. For us, as we study linear algebra, that's why we sort of group vector spaces into two groups, finite dimensional and infinite dimensional. In fact, many courses at the undergraduate level are restricted to only finite dimensional vector spaces. But the countably infinite dimensional vector spaces are not that hard to deal with, and they're important. The polynomial space, the sequences with finite support, are infinite dimensional vector spaces, but their bases are only countably infinite, so we can deal with those. So when you restrict attention only to finite dimensional vector spaces, you can't talk about those vector spaces, and that's too much of a loss, I think. It's not hard to see that if S is a subspace of V, then the dimension of S must be less than or equal to the dimension of V. And I'm going to let you fill in a formal proof for that. But you have to be careful not to jump to any hasty conclusions. For example, if the dimension of the subspace is equal to the dimension of the space, that will imply that S equals V only in the finite dimensional case, only when V is finite dimensional. And I'm going to leave that also for you to prove. And you have to prove that when V is finite dimensional, if the dimension of a subspace is equal to the dimension of V, then the subspace is all of V. And produce a counterexample to this when V is infinite dimensional. Here's a very useful formula. In the case of finite dimensional vector spaces, for the dimension of the sum of two subspaces. It's the sum of the dimensions minus the dimension of the intersection. This formula might look vaguely familiar to you. There's a version for just cardinalities of sets, nothing to do with vector spaces. And it's called the principle of inclusion-exclusion, and it generalizes. So this is the analog of that. In particular, when S and T are essentially disjoint, this becomes a direct sum. The intersection is trivial, dimension 0, and we have this very nice formula. And if V is the direct sum of S and T, then we can write it this way. The proof of this is not very nice, really. It's just sort of grinding out the proof using bases. So let's go through it. Suppose we start with a basis B for the intersection of S and T. We can extend B in two directions. We can extend it to a basis for S by including vectors A1 through AK, the A vectors. I'm going to call these the B vectors, and then these A's here are the A vectors. We can also extend B to a basis for T by including the C vectors. We want to show that the union, that all these vectors, the A vectors, B vectors, and C vectors, together form a basis for the sum. They certainly span the sum, because any vector in S is a linear combination of the A and B vectors. Any vector in T is a linear combination of the B and C vectors. So any vector in here is the sum of a vector in S and a vector in T. So it's a linear combination of all of these. The testy part is to prove this is linearly independent. So suppose we have some linear combination equal to 0. And I've used Greek letters for the coefficients. If I denote these three sums by A, B, and C respectively, it looks like this. And I've hidden all the complications of this up here. And little a is in the space spanned by the A vectors, little b is in the space spanned by the B vectors, and similarly for C. Now if I isolate A, I get A equals the negative of B plus C. This is in the intersection, S intersect T. Because B plus C is in T, it's a linear combination of the B vectors and the C vectors, which span T, but A is in S. This intersection is the same as this, which is trivial, because the A's were joined to the B's to get a bigger basis. So these two subspaces are essentially disjoint. So A is 0, and therefore B equals negative C, but that means this vector is in this intersection, which is trivial, and so all three, A, B, and C, are 0. So this union, A union B union C, is a basis for S plus T. Finally, if we take the dimension of S plus the dimension of T, it's the size of a basis for S plus the size of a basis for T, and that's the same as this, because A and B are disjoint, B and C are disjoint. Looks like this, rewritten like this, finally this. And that's the formula.